Well, hello everybody. I hope your summer's going really well, and if you're like me, you probably haven't thought a lot about math lately, and I have to confess I had to do quite a bit of prep work to kind of get my brain back in the groove just for this video here. But I brought up a few pictures. We did a little bit of traveling since I saw you last in video number 2. We got out we kind of swung through the Midwest with my travel baseball team, and we had pretty good luck. We came back with a little bit of hardware, and then after the tournaments we swung through Chicago, and I fell in love with their deep dish pizza. It absolutely changed my life, and I've been craving it ever since we got home. But we got to visit Wrigley Field, and I was representing my Hamburg gear there right down on the field, and we even got lucky. We caught a foul ball while we were there, and of course we took in some other sights of Chicago, and we saw the famous bean or whatever you call it thing. It was kind of neat. So anyway, we had a really good trip. We've had a fun summer so far, and looking forward to enjoying the last few weeks. But we're going to dive into some pretty interesting things today. The polar coordinates, we're going to keep it simple, but it's just a different way of thinking. We're so used to thinking in terms of rectangular coordinates, or a lot of times what I call Cartesian coordinates, and we're going to try to kind of turn it around and kind of learn a new language that we call polar coordinates. So the first thing I want to do is I want to go over how we're going to derive the big 4 rules. And I believe they are at the top of your sheet, and hopefully they look really familiar. But I'm not really big into memorizing. And so I want to kind of give you an option of how do we derive these so that we don't have to memorize them. And we're going to start off with the old Cartesian system that you're used to. Probably never called it the Cartesian system, but just because it was the only way we knew how to do things. But we had this x-axis and this y-axis, and what we did is we started right at the origin. We said, you know what, we're going to move to the right x units, and then we're going to go up a certain amount of units, and we'll call that y. And so you landed at this point up here, and we called that ordered pair x comma y. And what we want to talk about is how we're going to convert that into polar coordinates where the r comes first and the angle theta comes second. So we're going to kind of construct our right triangle here. We started at the origin, we walked to the right x units, we said, and then we went up y units. And you can kind of see the makings of a right triangle starting to come to the surface here. And then we'll go ahead and we'll draw in that radius, or the hypotenuse. Now the difference with the polars is instead of going to the right and then straight up, with the polars what we're going to do is we're going to start facing 0 degrees, and then we're going to rotate a certain amount of degrees theta. And then once you get rotated, you can march straight forward r units. Now, if this picture makes any sense at all, this picture alone is going to help you derive the big 4. Okay. First of all, the Pythagorean theorem says that the x squared plus the y squared has to equal the r squared. Okay. And now we're going to call on a little bit of trig, and I'm going to use SOHCAHTOA for the rest of my 3 rules. And hopefully you feel comfortable using SOHCAHTOA. I'm going to say that the tangent of theta equals the opposite divided by the adjacent, y over x. So there's a very popular one. Number 3, I could say that the sine of theta equals opposite over hypotenuse, which in this case is y over r. Now we usually don't stop there. What we do is we solve for y, and we say that y is equal to r sine of theta. So there's the third of the big 4. And then the last one just says that the cosine of theta equals the adjacent divided by the hypotenuse. And again, we don't stop there. We solve it for x, and we say x is really equivalent to r times the cosine of theta. And there you have it, ladies and gentlemen. There's the big 4. If you feel more comfortable memorizing, I'm not going to stop you, but I think it's, kind of, eases your mind a little bit. If you can kind of visualize this diagram and you feel comfortable with it and it makes sense, you could easily derive those 4 rules in the middle of a test. So the first thing I want to practice is just converting a Cartesian coordinate or a rectangular coordinate. That's just a fancy name for the ordered pairs that you've always used your entire life. I'm going to convert it into a polar coordinate. And the first point that I want to throw at you is the ordered pair 3, -3. And of course, like I said, that's a rectangular point with an x and a y coordinate. So as far as finding the r, I always think that's the easiest. We're just going to use the first rule on our list of the big 4. And we're going to say that r squared equals 9 plus 9, so we got r squared equals 18. I got r equals radical 18, which I simplified to 3 radical 2, so there's that. Now as far as finding theta, I always jump on the tangent rule that says I'm going to take my y coordinate divided by my x coordinate. Now here's the trick. When you go to solve for theta and you do inverse tan of -1, it's very important to be able to visualize that ordered pair and what quadrant it was in. If we had plotted that point, we'd have gone to the right 3 units, down 3 units, right? So we're sitting in the 4th quadrant. So being able to visualize the fact that that's in the 4th quadrant, that's going to help me decide that theta needs to be 7 pi over 4. You know, because of the 1 here, I knew my reference angle was 45 or pi over 4, and I just had to subtract it from 360 or 2 pi to get that 7 pi over 4. So my ordered pair is going to be 3 radical 2 comma 7 pi over 4. Now, of course, we're going to get into multiple representations later. You could have said 3 radical 2 and negative pi over 4, and that would be an equivalent acceptable answer, and I wouldn't say, you know, either one's better than the other. Our next problem, I want to take a polar coordinate and I want to convert it into a rectangular or a Cartesian coordinate. Now, what I'm going to do is I'm going to start off very simple. I'm going to say the R value is 4 and the theta is 150 degrees. Now, you know we usually don't use degrees. We're going to need to get in the habit of speaking in terms of radians for all of our angles. It's really the only language we use with regards to angles in this class. And I'm going to use the other 2 rules that I didn't use in the last problem. I know that the x-coordinate is always going to be equivalent to r times the cosine of theta, which in this case is going to be 4 times the cosine of that angle. Now watch, be careful here. You've got, now the cosine of your reference angle is pi over 6, that's 30. Cosine of 30 is radical 3 over 2. Now you got to be careful because 5 times pi over 6 is really 150 degrees. And because that angle lives in the 2nd quadrant, we're going to negate that value. And I ended up with -2 radical 3 for my x-coordinate. All right, I'll switch colors here real quick. The y-coordinate is going to be r sine of theta, which, let's see, that's going to be 4 times the sine of 5 pi over 6. Good news is this one's actually going to stay positive because the angle again is in the 2nd quadrant still. Pi over 6 is my reference angle, 30 degrees. Sine of 30 is 1/2. Like I said, we're going to keep it positive because we're in the 1st quadrant, or I'm sorry, the 2nd quadrant. And there's my y-coordinate. So this ordered pair in polars is really equivalent to -2 radical 3 comma 2. One of the things you're going to hear me talk a lot about throughout the years, you know, what are the little itty-bitty differences that separate really good math students from the great math students? You know, what separates the 4s from the 5s on the AP exam? Well, one of the abilities is to like just instantly visualize this. Nobody's going to force you to sketch that point, but the moment you set eyes on that, could you kind of visualize it and kind of get a ballpark of where it fell? You know, if I started off facing 0 degrees and I rotated 150, I'd be kind of facing that way. And then I'd just march 4 units forward and I would land right there. So if you get in the habit of just visualizing that ordered pair instantly, then you get this answer. Does it make sense that the x-coordinate's negative and the y-coordinate's positive based on the fact that you're visualizing that point right there? Of course it does. In fact, if your x wasn't negative or if your y wasn't positive, there's a red flag and you know you did something wrong. As far as converting equations now, so we're kind of graduating from points to now up to equations. I'm going to throw 2 real easy ones at you here to get you warmed up. The first one is, what if they said x squared plus y squared equals 4? Well, you look at your list of the big 4 rules, okay? And you instantly notice that this quantity right here, x squared plus y squared, is equivalent to r squared, which then means r equals 2, and that's just a really nice simple circle whose radius is 2 no matter what the value of theta is. So it's centered at the origin, and you hopefully surmise that just by looking at the original rectangular equation. The second example I want to throw at you, it says that 3y minus 7x equals 10. So here's a very nice linear equation. And when I get into this converting pattern, I always substitute r, let's see, that would be sine of theta for the y value. I had to catch myself there. And then whenever I see an x coordinate, it's really r cosine of theta equals 10. What I'd like to do now is I usually like to solve for r if possible. So I'm going to factor out my GCF of r, which then leaves me with 3 sine of theta minus 7 cosine of theta. And then I'm just going to simply divide that large obnoxious quantity to the other side and solve, get this r all by itself. So r is really equal to 10 divided by 3 sine of theta minus 7 cosine of theta. There it is. There it is. Moving right along, now I want to take a polar equation and I want to convert it into a rectangular equation. And so the example I came up with here says that r equals 4 sine of theta. All right, and this is kind of an interesting one. What I did is I went back to my list and I recalled that the y-coordinate, okay, the y-coordinate is really r sine of theta. We'll go ahead and divide the r over, and you get something like this. And so what I'm going to do is I'm going to use that substitution right there. I'm going to take y divided by r, substitute it in for sine, and see what that looks like. And you're thinking to yourself, well, oh goodness, what did I just do? I want to erase that. Okay. All right. Well, I didn't accomplish a whole lot, but I did. I got rid of the thetas, and that's a big step. Now I'm going to multiply both sides by r, and that's going to give me r squared, and over here it's just going to kill the r that was in the denominator, give me 4y. And then I could say, well, r squared is equivalent to what? According to the first rule of the big four, x squared plus y squared. And ladies and gentlemen, here we go. And I'm not going to worry about solving for y or solving for x. I'm very content right now with the fact that my equation is in terms of x's and y's only, and there are no r's and there are no thetas in it. Alright, now for my favorite part of the video. This is the favorite part of the homework sheet that I gave you. I think it can be rather thought-provoking, and I encourage you to be creative here, because even though I asked for like 4 ordered pairs, I believe it was, there's an infinite amount. And so, feel free to challenge me and make my grading a little more difficult if you want. But what I want to do is I want to go back and I'm going to pull out the ordered pair we used earlier, 4 comma 5 pi over 6, and we're going to challenge ourselves to come up with multiple representations of the same point. We're going to come up with other ordered pairs in polar form that are equivalent to this point. And so as I plot that point, what I always do is I pretend that I am facing the 0 direction, 0 degrees, and then I rotate myself 5 pi over 6, and once I rotate myself, I march 4 units forward. Now what I'm going to do, just for scaling purposes, is I'm going to pretend that each circle is equal to a half of a unit. Or in other words, 2 circles equals 1 full unit. So as I march forward, that would be 1, this would be 2, this would be 3, and this would be 4. So there's my point right there. And we rotate it in this direction right there. So as we try to come up with multiple representations of that particular point, we're going to play with the angles, we're going to play with the r values. One of the things that I can do is I could rotate clockwise instead of counterclockwise. What if I rotated negative 30 degrees, okay? And then once I rotated negative 30, what if I walked backwards instead of forwards, okay? So I'm thinking to myself, negative 4, negative pi over 6. There's an example where they're both negative. So just to recap that, let's see, where's my little highlighter thing? Is that him? This might be it. Yep, there it is. Okay, so I started at 0. I rotated clockwise 30, which is negative 30, and then instead of marching forward, what I did is I went backwards 4 units, and then hence the negative on that rascal too. Okay, what else could I do for a representation? I could just continue to rotate in that clockwise direction. Instead of just doing negative 30, why don't I go all the way around here? And so as I go in this clockwise direction, there would be 180, and then once I hit 180, I went an additional 30, so that put me at 210, and I know that 210's 7 pi over 6, and once I got there, I went forward 4 units. So there's another representation. And again, like I said, there's an infinite amount of answers, but the last one I'll throw at you is, what if I did go in the normal direction? I rotated in the counterclockwise direction, but instead of stopping at 150, I continued to rotate until I hit 330, okay? What if I went all the way to 330? Once I hit 330, I wouldn't go forwards 4 units, I would then go backwards 4 units to hit there. So what I'm doing is I'm going negative 4, but I'm rotating 330 degrees, which I believe is 11 pi over 6. So what I've done is I've created a list. This should hopefully spark some thought anyway. Here's a list of 3 ordered pairs anyway that are equivalent to this one. If I plotted them all, they would all land right there, yet they certainly look different depending on whether you rotated clockwise, counterclockwise, you walked forward 4 units, or backwards 4 units. So as always, I hope that helped a little bit. Good luck with your assignment. The good news is the third one that you're working on right now is the hardest, I believe, of the four, in my opinion. And the good news is the fourth one, the only one you have left, is ridiculously easy. And I feel very guilty, and I have trouble sleeping at night knowing that I gave you such an easy one. But take advantage of it, enjoy it, and we'll see you soon.